Good afternoon, one and all. Welcome to session 5, which is the last technical paper presentation session for today. First of all, I would like to welcome our session chairman, Shri A. Devdas, ex-ED Operations SAIL, and I request our rapporteur, Shri Tapas Das Gupta, CJ in charge Iron BSP SAIL, to escort him to the dais. I welcome our speakers for today. Shri Kushal Agarwal from Sarvesh Refractories to the stage. Shri Pranay Kumar Yadav and Kumar Gaurav from Jindal Stainless Limited. And Dr. Rahul Jain from IIT Bhilai. Presentations in this session. For each presentation, we will be giving 10 minutes of time. The first bell will ring at 8 minutes and the second at 10 minutes. Without any further ado, now I request Shri Kushal Agarwal from Sarvesh Refractories to present on forging self-reliance with innovative refractories for the steel industry.
Good afternoon, everyone. Respected dignitaries, ladies and gentlemen, I would like to first start by thanking the organizers for giving me the opportunity to speak at this forum today. Obviously, we are gathered for a very important topic, which is decarbonization. That is the topic of the moment. Everywhere I go, we are talking about decarbonization. But I believe, along with decarbonization, self-reliance is also very, very important, especially when it comes to steel industry and refractory industry by extension. Today, I want to discuss why it is important for every aspect of the Indian steel industry to help India achieve its 300 million ton steel production dream in a sustainable way. How Sarvesh as a company is contributing to this journey, and what we believe are the steps for being a self-reliant and sustainable refractory industry. So, India is on the verge of being an economic superpower, and steel industry is obviously its backbone. Therefore, it's essential that the steel sector itself is self-reliant. So the question here is, what does self-reliant actually mean? How can we achieve it? It means the ability to sustain itself independently without relying on external resources. This is also an issue of national security. Becoming self-reliant has many advantages. Number one, obviously it will lead to job creation. It will obviously lead to fostering innovation and creating a value chain across the economy, leading to sustainable development of the entire economy. It also enhances one's ability to withstand global disruptions, ensuring stable outputs even in challenging conditions. As you are all aware, today the world scenario is more turbulent than ever. The entire Middle East is at war. Russia-Ukraine standoff doesn't seem to end. Even our neighbors, including Bangladesh, are more volatile than ever. Relationship with China is also not very sweet, and obviously we all know China has been and will always remain mercurial. So, if there ever was a need to focus on being self-reliant, I think it's now. Although refractories are a very small part of steel industry in terms of input cost, there is no way even a single kg of steel that can be produced without refractories. And hence, as I speak on a self-reliant steel industry, it is essential that refractory industry itself becomes self-reliant. At Sarvesh, we have embarked on a two-pronged strategy. First, and more importantly, is to substitute magnesia. When it comes to magnesia, we are not blessed with the resources like other countries, for example China and many other magnesia producing countries. I don't know if you know, but China alone produces more than 85% of magnesia that is used in our industry. Hence, to be self-reliant, it's important to nurture and use the available local raw material which we have in abundance. Not just in abundance, but in some specific application, it is more suited for that particular use, giving better life and obviously helping in overall reduction of carbon footprint. Second is to create infrastructure for critical refractories. For example, like for converter refractories, which historically and is still mostly imported from China and elsewhere from the world. Critical refractories especially should be developed in-house and manufactured here locally in India. This will foster innovation and will lead to a sustainable development of the whole economy and will also ensure minimal disruptions in terms of supply chain. So, how are we replacing magnesia? How is Sarvesh replacing magnesia? Well, as we all know, there are mainly two kinds of steel, flat steel and long steel, which in turn is either aluminum killed or silicon killed. In aluminum killed steel, magnesia is being effectively replaced by refractories like annular spinel, especially in the metal zones of steel ladles. This has major advantages. First being, obviously, it's an indigenous raw material. The main constituent that goes into making alumina spinel is white fused alumina, which is being made in India, and the raw material for making white fused alumina is also available abundantly in India. It also helps in achieving overall efficiencies. For example, you can reduce your lining thickness even by increasing life. There is no compromise in life, and you can still improve all the operation parameters of your steel ladle. Similarly, in silicon kiln process, you can replace it with dolomite. We have already developed dolomite refractories for the same. This is also replacing magnesia in a big way, and I believe it's an excellent refractory solution for long products. In fact, SAIL is one of the early adopters of these industry advancements. Plants like Bokaro and Rourkela Steel have already started using alumina spinel bricks in a big way. This has not only increased the ladle volume, but has also increased life, and truly in a very indigenous way by use of indigenous raw materials. In fact, very recently we achieved the highest ever life at Bokaro Steel of 160 heats and an average of more than 150 by using alumina spinel, which earlier used to be around 110 heats in a traditional magnesia carbon lining. So you can see there is a huge advantage both in terms of life and also ladle volume, which both helps in reducing carbon footprint. Similarly, Durgapur and Burnpur Steel Plant, ISCO, have used our dolomite refractories and have gained significantly. There has been an increase in life with complete use of indigenous raw materials of dolomite. All this leads to carbon footprint reduction in a big way, while using indigenous resources, which is more important to have a sustainable steel production. Coming to stainless steel, which is again highly dependent on dolomite refractories, stainless steel, as we all know, is gaining a lot of importance strategically right now. A lot of construction material is being now replaced with stainless steel. We heard someone speak about how bridges is being, in bridges the stainless steel is being now used to make bridges. Some of you would be surprised to know that more than 30% of the 30% of the refractories that is used in AOD, in terms of dolomite refractories, is still being imported, in spite us having all the resources in India. Most of it is imported from China. Even though we have the resources, we are still importing. Just imagine the loss of forex and opportunity of value addition that we are losing in India. Sarvesh has invested and is putting a lot of focus on changing this. We are aiming to reduce imports and achieve self-reliance in this critical area. With growing need for stainless steel, the strategic importance of this is ever growing. Now coming to BOF converter refractories, as I said, it is still and being mostly imported from elsewhere. Our target is to serve the world now. We are growing strength to strength with our world-class facilities and are able to match global standards, competing against the best in the world. There was a time when Indian steelmakers didn't rely on India-made BOF refractories for their converters. But this is quickly changing. With the indigenous development, we see an amazing demand for homemade converter refractories. Time has come not only for Indian steelmakers to use made in India converter refractories, but also for India to become an exporter of refractories and become a global hub for converter production. In conclusion, self-reliance in the refractory industry is not just a goal. It is a pathway to strengthening India's position in the global steel industry. Sarvesh is at the forefront of this innovation, leveraging local resources and contributing to nation's strategic goal of being Atmanirbhar. Our mission is to develop world-class infrastructure in India to produce top-quality products by ensuring 100% value addition within India using local raw materials. With a vision to position India as a global leader in refractories. This will not only support India's goal of becoming a superpower, but also transform India into a hub that supplies innovative refractory solutions to the entire world. Thank you again for giving your valuable time and being such a patient audience. Thank you so much.
Thank you, Shri Kushal Agarwal. I now request Shri Pranay Kumar Yadav and Shri Kumar Gaurav from Jindal Stainless Limited to present on development of low chromium ferritic stainless steel grade IRS 350 CR and its use in structural applications.
Good evening, everyone. Myself, Pranay Kumar Yadav, and along with my colleague Kumar Gaurav, we will be presenting about the topic development of high strength stainless steel grade, which can be substituted to normal carbon steel that are prone to the more corrosion compared to stainless steel. So we will be presenting about this topic. We are from Jindal Stainless Limited, which is India's largest stainless steel producer and among top 10 producer of world, which is founded by Mr. O.P. Jindal ji, and we have the production capacity of 2.9 million ton at present. You can see in the picture, presently most of the foot over bridges are made from the carbon steel, low carbon steel with the high strength, which has the higher corrosion rate compared to the stainless steel. So, which require the regular periodic maintenances, and few are the places where the maintenance is not possible. We apply coating, we apply paintage, but that has the lower shelf life or lower life cycle. In this table, we can clearly see the corrosion test we have done, the salt spray test, in which we can see the carbon steel has the 19.55 milligram per area corrosion, compared to when we compare with the SS, which is the IRS 350, which has the 0.107%. So we can clearly see that there is a 200 times less corrosion in stainless steel compared to the carbon steel that is presently applicable in the most of the structural bridges or foot over bridges. So there were recent collapses of structural bridges. So one of the proposals from the railway, mostly the IRDSO, how can we substitute this carbon steel with the stainless steel? Keeping in that mind, we developed one grade which has the similar mechanical properties and impact toughness as the carbon steel and has the better corrosion resistance and also the lower life cycle cost. So first up, for developmental, we use the thermocals. For using the thermocal, we find out what are the phase fractions, what are the liquid phases which is present at what temperature. After that, the bell annealing cycle was designed at what temperature annealing is required. After that, the lab scale trial was done. Further, the plant scale trial was done and the material was dispatched for the customer application. We are primarily through the scrap route. So we have electrical arc furnaces, AOD, continuous caster, roughing mill and reheating furnaces. So first this is what the thermodynamic calculation using the thermocal. In this plot you can easily see what is the AC1 temperature which is required for the annealing temperature below which we require the annealing process to happen. So through this plots we can clearly see the AC1 temperature was 40 degrees Celsius and the liquidus temperature was approximately 1300 degrees Celsius. So above that we require the annealing parameters were designed. This was the chemistry, the range chemistry in which the alloy is designed for this grade. based on the AC1 temperature, we have done the two annealing cycles for 680 degrees Celsius and the 700 degrees Celsius for different time frames, 12 hours, 14 hours and 16 hours for both the temperatures, and this is the mechanical properties required from the RSDO, Railway Development Board. So nominal thickness and the YS should be greater than 350 MPa and UTS, and one of the major requirement was the impact toughness of greater than 34 joule at the 4 degrees Celsius. So based on these annealing cycles, the lab scale trial was done, and further the lab scale trial results will be shown by my colleague Kumar.
So coming to the microstructure, hot roll structure was observed. It was found that lab type martensite structure was observed, and then the material tempered at 680 degrees centigrade for 12, 14 and 16 hours. In 12 and 14 hours of soaking, the structure didn't change much. However, in case of 16 hours of soaking, the recrystallization started to occur. In such type of high alloy materials, more time is required, soaking time basically, because the diffusion process is very sluggish in such kind of high alloy elements. So now the hardness and mechanical properties were also determined for this annealing temperature, and it was observed that in this case also the hardness in HRB scale, it was determined that in 12 and 14 hours it didn't change much. However, in case of 16 hours of soaking, it came down considerably. In the case of mechanical properties also, YS UTS values came down with increasing of soaking time and elongation increased. The same activities were done for material annealed at 700 degrees centigrade, and it was observed that the recrystallization started to happen at 12 hours of soaking. However, in case of 14 and 16 hours, the grain coarsening started to occur, as ASTM grain size number was observed 7.0 to 7.5 in case of 16 hours of soaking. And hardness and mechanical property was also determined. In this case, it was observed that at 14 and 16 hours, the hardness value came considerably down, which was reflected in mechanical property also, that when the material soaked at 16 hours time, the values even came below the minimum permissible requirement, which is 350 MPa. Now further impact toughness values were also determined for both temperatures and all soaking times, and it was observed that the values which were achieved is considerably higher from the minimum requirements, which is 34 joule, and the impact toughness was done at 4 degrees centigrade. However, in case of 700 degrees centigrade, the values were higher as compared to the material tempered at 680 degrees centigrade. So based upon all such lab scale experiments, plant scale trial was conducted, and the material was soaked at 690 degrees centigrade for 12 hours, and one step heating was given to homogenize the temperature across the charge bed, and then further material characterization was done, and it was observed that the microstructure were composed of ferrite along with fine carbide structure, which is lighter phases, and along with this YS UTS elongation and hardness values were also determined, and it was well complying the minimum specified requirement. So further the ACM analysis was done for base material and after annealed material to verify the evolutions of carbide phase, and for this base material EDS analysis was done, and the chemical composition was matching with the material compositions. After that, after annealing, light phases were basically pointed out in ADS spot, and it was observed that carbide forming elements were observed, like moly, nickel and carbon were all richer when the EDS was spot. So from this the evidence was observed that ferrite and fine carbides were observed, which led to improve in toughness and elongation in the material. So coming to the conclusion part, increase in nickel and moly content in the material has resulted in increase of strength and toughness. So after optimization of a batch annealing process, microstructure with ferrite and fine carbides has led to the improvement in strength and ductility of the material. These is the few examples which are shown here in which IRS 350CR grade material is used, which is Naupada railway junction, and another one is Srikakulam road railway junction, which is in a coastal area situated in Andhra Pradesh state. Along with this, various Mumbai regions bridge projects are also undergoing in which this grade material is being used. So this way, grade IRS 350CR have been successfully developed and catered for bridge applications. So that's all from our side. Thank you.
Thank you, Shri Pranay Kumar Yadav and Shri Kumar Gaurav. Yes.
One thing is that we can have some question answer session also. If anybody has any question, please come up.
Hello. So you have shown that single step, and then at 650 degrees Celsius you are giving here. So from ambient temperature to 650 degrees Celsius, there will be temperature like between the core and the surface. So there will be thermal stresses development.
So we do this process in the batch annealing process, which is the enclosed surface, and we inject ammonia or hydrogen gas, which is as a heat carrier source. So that homogenizes the whole container in which we place the multiple stacks of coils.
Even though, because we are in the same field, so in my opinion, there should be one more step in between.
That can be, but in our case, we can achieve and also our batch process are, if you are stacking multiple charges.
So by doing that, you can reduce the soaking time also, that 12 hours, 14 hours, 16 hours. By doing that homogeneous temperature at the intermediate temperature, so we can do homogenization, that fine cycle structure.
Okay, sure.
Thank you.
Any other questions?
Impact of chloride on these chlorides. Can we use this water for seawater applications?
Yes, we can use. Mostly this is projected by or also promoted by the railway in the coastal areas, because where the salty nature of more salts are present. That's why we are adding the molybdenum.
But have you carried out some study where we have shown the graph that with the so much of temperature, these are chloride limits?
Yes.
About 80 ppm, 100 ppm, 150 ppm, 500 ppm.
Yes, the salt test is done for the multiple samples.
Because generally stainless steel is not able to withstand high chloride steel. Generally stainless steel is not able to withstand high chloride level. But the threshold limit.
Yes, there are multiple grades in which we can vary the molybdenum content or nickel content based on the requirement, which environment we are catering for the customer. So this is the mostly coastal area, so this can easily achieve the properties, corrosion properties with only 0.2 or 0.3%. But we make grade with the 3% of molybdenum. That can sustain, I think, the requirement you are asking. And also, if any specific requirement, we can collect that data and we can develop also if there is some requirement.
Any other questions?
Yeah, my question is how this IRS 350CR will help in reducing the carbon footprint? Whether it has got any direct link with the carbon emission or emission reduction?
Yes, I can quote that because we are stainless steel producers through the scrap route. So inherently our carbon footprint is much lower than the carbon steel. So we are certainly greener than the carbon steel. Again, the life cycle cost when we compare, that is quite low compared to the carbon steel. And also the recycling nature. More than 98% of scrap that are used can be recycled and used in our process. So inherently this process has the low carbon footprint compared to the any carbon steel that is used in this process.
Thank you, sir.
We are talking about the life cycle, better life cycle. What is the corrosion index of this compared to the plain carbon steel?
This is compared to the carbon steel.
Point.
0.107. This is the Sail-Bsp test we have done compared to the carbon steel.
Any other microbial corrosion test you do on this?
We can certainly do that.
Have you tried it?
Yes.
Because once we are going for this corrosion atmosphere, microbial corrosion is also one of the factor which affects.
Yes. We can do that test also, but inherently the material has the better properties in the mill scale also. So that property will be certainly higher than the carbon steel. We can guarantee that one.
Okay.
Thank you, sir.
Thank you.
I now request Dr. Rahul Jain from IIT Bhilai to present on an image-based deep learning model to predict surface defects on billets manufactured through continuous casting in steel industry.
So, good evening all of you, dignitaries on the dais and off the dais. So, I am Dr. Rahul Jain. I am working as an assistant professor in the Department of Mechanical Engineering at IIT Bhilai. So, the work which I am presenting over here is basically an image-based deep learning model which was used to predict the surface defects in blooms and billets. Because blooms and billets being one of the bread and butter for most of the steel industry. Right, so this is just a brief about IIT Bhilai because we are in IIT Bhilai, so most of you would be knowing. So, so we shifted last year only, and the campus is coming pretty good. So, few from BSP I know have visited, and I would like to extend an invitation other people who would like to visit for research collaboration or even visiting IIT. So, coming to the problem statement, so whenever we are making any product through any of the manufacturing process, defect by nature comes hand in hand with most of the manufacturing process. So, if you see in some of the figures, these are some of the figures of blooms and billet, where we can see different types of defect which are originating for various reasons, center holes, scratches, bed cut, etc. Now, so the basic idea was, can we come up with some kind of an online monitoring system, a non-destructive based one, where we can identify this kind of a defect so that the defective billets or blooms can be segregated from the correct ones. So the problem statement goes like this. So most of the steel industry where we had an one-to-one discussion, we understood whenever they are doing this continuous casting, because the billets and blooms which are coming are at a very higher temperature, most of the time the blooms and billets are visually inspected, right? And whenever this blooms and billet is going into inventory and all, we have a stacks of hundreds or maybe more than that of blooms and billets. So physically for a human being to assess all the defects, even which is on the surface, is very difficult. And if a defective billet or bloom is going for a subsequent manufacturing process, it lead to a low grade product, that is point number one, but it will also lead to lot of energy consumption, which could be avoided if we can discard this defective billet at the end of continuous casting. So the idea was very simple. If we can introduce a deep learning image based model in between for defect identification process, so wherever we have a defective billet, it can be discarded and only the billets which fulfills the requirement is sent for the subsequent manufacturing process. So with this particular idea, we started, and so when we discussed for blooms and billet, we were told there are various types of defect like center hole, pinhole, bed cut and all. So what we thought, we tried to club all these different type of defect in three categories. One was, we call it as hole, whether we call it as center hole, pinhole, blow hole, everything we categorized as one defect, we are calling it as a full defect. Then there is a bed cut, because whenever you are cutting these blooms and billet through gas cutting or any other method, there is an undulation on the surfaces. So that is what we are saying as a bed cut. And the last category is surface defect. So if there is a scratch on blooms and billet or certain kind of crack, that is what we are categorizing as a third type of defect. So what we did, because from whenever we are getting certain kind of images from industry, there are multiple blooms and billets which are stacked over there. And when we want to process it, we face lot of challenges, because that focusing on a particular billet becomes a challenging part. So what we did this pre-processing of the images which we got, what you see over here. So first we did the background subtraction. So apart from the bloom which we want to inspect, whatever additional information is there in that particular image, that was removed. And then we did certain rotation, because when this blooms and billet is being moved in a conveyor belt, right, nobody is ensuring the orientation and all those things. So we did as per the requirement, and some results has been shown in this particular slide. So, and then for any deep learning model, one of the important aspect is the training of the data set. If the training is appropriate, then the accuracy of the model can be ascertained. So what we did, we collected certain images of blooms and billet. We manufactured certain defects by drilling the holes on the steel plate and all, and certain information we took it from internet. And then we used image augmentation technique to increase the number of images. So eventually we end up getting close to 300 billet images, the cross section of it, and then we train. So the figures which you see is basically for the training set, where we predefined, okay, if this kind of a shape is coming, this is a porosity. If there is an undulation or something, then it's a bed cut, so on and so forth. So that is a methodology. So this is primarily what we did. So we tried with 320 pixel image, we also tried with 640 pixel image. The idea was very simple. We wanted to try with the kind of image which we can even take with mobile. If you have a higher resolution, obviously the accuracy will go higher. But the initial thought was, even if it can take a photo with mobile, because nowadays everybody has a camera mobile phone. So that is where we started with 320 image size, which is basically the 320 by 320, and then 640 by 640. So whatever image size we got, first we tune it down to 320 by 320, and the part which we did for 650 pixel size, we tune it down to 640 by 640. And in between, what you see as CNN, that is basically a convolutional neural network method that is basically based on YOLO, right? So we did certain parametric analysis, and this is by and large the methodology in one slide, if I could have mentioned. On the left hand side, you can see the cross section of three billets. In between, we have this object detection model which is based on CNN method, right? Certain parameter detailing I'm not going into just because of the time constraint and all. And at the end, if you see the images on the right hand side, if you match each of them, the model was able to accurately predict different kinds of defect. So red colored rectangle which you see on the top right side of the image, it is basically indicating the holes, which is pretty much visible at the boundary surface of the billet. Same goes for the bed cut and surface defect. I'll show some more results. So this is a parametric thing. So one of the major concerns which we had was there should not be any false prediction. False prediction meaning there is no porosity, there is no defect, but still the model is saying there is a defect over there. So we did extensive iteration by changing different parameter. So the red color graph which you see is basically indicating the false prediction, right? So if you see for certain value of x-axis, which is some value we are calling it as confidence level, for different images, so image 1, 2, 3 and 4, for lower and higher confidence level, you can see there is almost zero red color bar, which is basically indicating the false prediction is almost pretty much close to zero, right? But for certain different value of confidence value, we still have certain false prediction. So obviously from this entire analysis, we came up with, for different image size, we come up with a particular value of epoch and particular value of confidence. And then with this, we tried to test our model with different things. So this is one image we created. So we did a very simple thing. We had the steel plate with micro drilling and normal drilling. We created lot of holes. So that is what you see in figure A and C. So figure C, whatever numbers you see from 1 to 11, those are micro holes. Micro holes of the order of 100 micron and 200 micron. Because we also wanted to check our model in terms of up to what resolution the model can predict. Right? And the image A, if you see, so from 1 to 5, those are the holes which are bigger in size. So of the order of an of that kind. B and D is the respective predicted image, right, where you can see almost all kind of blowholes were predicted by that particular the model which we developed. Then we wanted to test with actual image, because when we are taking the actual billet, lot of things get changed, the surface profile of the image and all those things. So if you see, the image A is basically only having a bed cut, there is no porosity. That is why if you see this orange color and pink color box which is indicating the bed cut defect, which we introduced the color code over there, that is there and there is no porosity defect. But if you compare image E versus F, right, you can see a lot of porosity defect over there which we counted, which was coming out to be close to 18, and you can, the corresponding image is F. You can see lot of red color rectangle over there which is basically predicted by the model. So we said we should have some kind of a color coding to understand whether it is a porosity or bed cut or what kind of defect it is. Right? Similarly, C versus D, C is basically just showing the bed cut. Because of the gas cutting, there is some kind of undulation. Similar thing was predicted. You see this pink color box. Similarly, G versus H. Right? So the idea was very simple. The idea was to start to test this model with a image which are perfect images, and then shift to the kind of images which the actual billets and blooms will have. Right? So this is just simple. I tried to avoid the lot of technical jargons and all those things. So with this, we tried and testing close to 20 to 30 billets, and we achieved pretty much good accuracy. So in conclusion, we can say we developed a defect identification model which can predict the surface defect. Even this model is capable of predicting porosity of the order of 100 to 200 micron, which I showed in one of the results where we did this microdrilling, and obviously of the order of as well. Right? In certain cases, obviously there was some amount of false prediction which we tried to avoid by the process optimizations. So thank you very much. So if there is any question, I would be more than happy to answer.
Thank you, sir. Any questions for sir or for the presentation by Service Refractories are welcome.
Sir, I would like to ask that in most of the cases, in our case, I am in ring mill and there we are dealing with blooms. In most of the cases, the blooms are covered with scale. Means the defects are not visible to naked eye. Means our cases we don't encounter these holes and all that, but some underlying cracks and some irregularities in surface that we do encounter. So how to deal with these kind of things? Can your model deal with these kind of things?
So these images which I have shown, we have not done any kind of post-processing or anything. It is just the images which we got it from industry, basically from ESP only. So these are the actual images. So I hope whatever scale and all those things would be there, it would be there in this. If you can show me some of the images, maybe I would be able to tell you with more confidence whether it is possible or not. But we tried with some extreme condition images. Although there was some deviation in accuracy in terms of in these cases, if there are 10 defects, we were able to predict 8 to 9. If the image quality or if the surface quality is bad, maybe that can hamper a bit here and there. But I think it should be possible. I don't see any reason why it should not be.
And secondly, you are showing only the defects that are present or visible on cross-sectional side.
Yes, sir.
What about the entire surface?
So top surface also, it's a possibility. Internal defect we are not talking it about over here because it is not possible with that particular model. But even if it is on top surface or any of the surface, it can be done. Because the image we had, we did it. Some of the images which we took from internet, we tried for the top surface as well or the side surface.
Okay, thank you.
Any further questions?
any standard model that it gives how much accuracy?
No, I have not checked with any standard model. What I have checked with is when I have got a particular defect, I have tried to see if there are X number of defects. My model prediction is how close to X. So if there are 10, if I am able to predict 8 or 9, because here it's not only about prediction, it's also about classification. And also I need to look for the time, because in industry, if the conveyor belt is moving and my software is taking, let's say, 1 minute time to process it, it is of no use. So apart from accuracy, faster prediction is also one of the important criteria for this. So standard model, I have not checked, to be very honest, but accuracy sense I can say we have got somewhere between 80 to 90%. Thank you.
Have you developed some scanning system for this? Like if you want to scan the image online for a typical, say, 6-strand broom caster or billet caster, can you do it? And number two, till at what temperature can you put this in practice?
I'll answer the second question first. The images, as the moment we start seeing the cross section in grayscale, this model will work. So because in steel, even at 200, 300 degrees centigrade, we can see in grayscale. So that is one. So it will work that way. Hardware part, the requirement for this particular thing is a good quality camera, right? So we are working in the hardware and we are working also in certain things, so we are able to make a ready-made solution kind of thing. So software part is complete. Hardware, we are still trying to figure out a good company from where we can get a good quality camera. So that's a work in progress. I assume it will take another 3 to 4 months time.
And that is to be put in for each strand?
Wherever we want to put it, yes.
Because normally after the blooms come out of the caster, they come to a bed and then they are separated. So
yes.
Within that time you have to scan it.
Yes, sir.
Another thing I want to ask is that in blooms especially, there are double pore defects, fine double cracked lines which are there on all sides, like right from the top to bottom. So can it scan this thing?
Yes, sir.
Very fine defects.
Yes, sir. It can.
Normally some of them are not visible by naked eye.
So that's why, sir, that is why I wanted to have holes of the order of 100 micron and wanted to check my software with that. So up till now, whatever I have checked, it can. If you have some image, you can send it to me and I can send you back the results maybe in a day's time. Just to give a confidence building that yes, it can do.
Not many questions asked. We have 3 sessions here. In the last session, we have 3 presentations. One by Sarvesh, another by Jindal Stainless Steel, and third one is by IIT Bhilai, Rahul Jain. So I will request our session chairman, Devdas sir, to please sum up.
Thank you, Tapas. A very good afternoon or good evening to all of you. I think there is a fatigue factor already creeping in among the audience. So I'll just keep it short. We had, in line with whatever presentations we had in the morning and in the afternoon, early afternoon, another lively and interesting session here with 3 presentations out of the 5 which were originally scheduled. Like Tapas said, the first was by Mr. Agarwal from Sarvesh Refractories on the subject of forging self-reliance with innovative refractories for iron and steel industry. During all the discussions that we had throughout the day, focus was on what you call new technologies or developing technologies for reducing carbon footprint, and we had earlier sessions where some of the other speakers had spoken on the what you call indirect development of the requisite refractories which were in line with the requirement for the modified processes. So in continuation with this, it's quite appreciable that we see Sarvesh Refractories also coming up in this line. And I was just discussing with Mr. Agarwal, and he was mentioning that Sarvesh is probably the only Indian refractory manufacturer in the fray right now, after the multiple takeovers which have taken place recently. And it is appreciable that they are constantly endeavoring to substitute imports by indigenously available refractories, trying to lower costs, and also increasing the increasing the life, thereby reducing the carbon footprints again. Some of the interesting things that he said was in the area of red refractories, where aluminum kiln and silicon kiln applications for which refractories they have been developing. And more importantly, I felt was the development of indigenous BF refractories. For many years now, we have been very highly dependent on seawater magnesia imports, especially from China. There have been many occasions when the supplies have been very unpredictable, and we have been put to various hardships getting the material. So the initiatives taken by Sarvesh, which were clearly brought out by Mr. Agarwal, would go a long way, I believe, in inducing self-dependence. Indigenously developed refractories would go a long way in reducing our costs, because refractories form a bulk of the costs in the steel making field. And any appreciable effort that can be made in lowering these costs would go a long way in sustaining the steel making process. Thank you for your lucid presentation. The second presentation was by the team from Jindal Stainless. The development of low chromium ferritic stainless steel grade IRS 350 CR for use in structural applications. It was good to see that they had, in response to multiple failures of foot over bridges in different locations, they worked on the development of this particular grade as a substitute for carbon steel structural application steels. They have explained very much in detail how they have developed this product, what all tests they have done, expecting lower life cycle costs by going through different annealing cycles, in-depth trials, addition of various alloying elements, and optimizing the annealing process for higher strength and ductility. I hope that this will be a really successful substitute for the structural steels that have been used till now for foot over bridges. And I hope that you will be also developing more steels for other applications also. So good to see your work. Thank you. Lastly, we had a very interesting presentation by Dr. Rahul Jain from IIT Bhilai. This subject is of more interest to me also, as I have been working with SMS for more than 30 years. And detecting defects on blooms and billets, with minimal manual intervention, that would be something that we would all long to see. But as far as I could see, this is still a work in progress, what you're doing. I think you need to interact much more with the industry, and probably, it would be my humble suggestion that more interaction with our own steel shops in Bhilai, SMS2 and SMS3. I think there were a lot of interest shown by the people here, also from quality, Mr. Shankar. So you probably get a better idea of what the industry is looking for. What you're trying to do is, of course, whatever we have gleaned from experience of the industry. But if you interact with the people directly working here in SMS2 and 3, I'm sure that the model that you are trying to develop, it would be a 100% success, and it would be of great use to our own people, the steel fraternity here. Thank you. So it's been a very, lively and interesting session, lots to learn. And I'm sure the audience also had a good time listening to all this. And thank you, Tapas and the organizing committee, for having me as the chair for this session. Thank you.
Thank you, sir. I now request our session chairman, sir, to kindly felicitate our speakers for today with a memento. Shri Kushal Agarwal from Sarvesh Refractories. Shri Pranay Kumar Yadav from Jindal Stainless Limited. Shri Kumar Gaurav from Jindal Stainless Limited. Dr. Rahul Jain from IIT Bhilai. I now request our rapporteur, Shri Tapas Das Gupta, everyone for dinner at Bhilai Club at 7:30 hours. Thank you.
One more announcement, please. All delegates are requested, if possible, they can collect their gifts from the counter outside this hall. Please.
सर पीछे के नहीं देख रहे
ये दो चार लोग अच्छा बैठ जाए क्या कुछ लोग बैठ जाए क्या
हाँ बैठ जाइए नहीं ठीक है